We're going to do this problem number 2 here, but we're going to actually start by talking about special right triangles and then go back to that problem. So this idea of special right triangles, there's 2 kinds. And we're going to put it on the bottom of the paper. So on the bottom of the paper, draw yourself a right triangle with 2 equal legs. Does anybody know what the special name for this special right triangle is? Desmond.
Isosceles?
Just plain isosceles?
I think it's an isosceles.
So there's isosceles triangles, of course, but this
that's 45, 45, 90.
So that's one of them, 45, 45, 90. When you have the 2 sides being equal, you learned in geometry, if 2 sides of a triangle are equal, the opposite angles are equal, and if one of them is 90, they both have to be 45. So there's a 45, 45, 90 triangle, but there is another name for it besides just isosceles or besides just right triangle. Isosceles right triangle. That's the name. Okay. Okay. So if you're looking for something more exciting than that, but isosceles right triangles are 45, 45, 90 triangles. So you can use that terminology interchangeably. Isosceles right triangles. Okay. So if this side is n, then this side is n. You guys know what this side would be then? Oh boy. N root 2. Okay, you guys do know the difference between squaring and square root, right?
Yep.
Okay, because I heard a lot of squaring there. Is this what you meant, though?
Yeah.
Okay. Okay. I don't have to explain the difference. Okay, that's n root 2. Now, what we said last week is that when you talk about right triangles, these are the nicest right triangles in terms of numbers and angles. If you have something like a 3, 4, 5 triangle, the sides are whole numbers, but the angles are definitely not whole numbers. In these triangles, the angles are whole numbers. These are whole numbers, potentially, and this is going to be irrational. There are no triangles that are right triangles with right angles where all the sides are whole numbers and all the angles are whole numbers. They just don't exist. Okay? So these are the nicest types of right triangles if you're talking about sides and angles. And then there's another type that is also nice. What's this other type going to be called? Do you know? 36-90 triangle. Those don't have another special name. They don't have an alternate name. One way to think about 30, 60, 90 triangle is take an isosceles triangle and split it in half. Whoa. Take an isosceles triangle. Sorry, I'm saying it wrong anyways. Take an equilateral triangle and split it in half, and that's where you get a 36, 90 triangle from. So it's half of an equilateral triangle. Okay, let's see if you remember this. The key side is the one across from the 30. We call that n. What do you call the hypotenuse? Or what do you label the hypotenuse? Or how long is it compared to this side? 2n, yeah. So the side across from the 30 doubled is the hypotenuse. So if this was 5, this would be 10. And then what's that third side? N root 3. And these are the 2 special right triangles. You should try to memorize them if you never have. They're the basis for a lot of the things that we do. The reason that we use special right triangles is because, again, these are the easiest triangles to do trigonometry with. They might not seem like they're easy, and I'm not going to tell you that it's easy for everybody because it's not easy, but they're the easiest type of right triangles, and that's why you learn with these triangles, even though when you apply trigonometry to real life things, they're not always going to be just 45 degrees and 30 degrees and 60 degrees. It's just when you're learning, these are the best angles to work with. So this one says, find the sine of pi over 4. Now, you might not know this at this very moment, but you will, that pi over 4 is 45 degrees. So sine of pi over 4, sine of 45 degrees would be the same thing. And we can look down at this triangle and pick either one of these 45s because it wouldn't make a difference. And we could say, let's do opposite over hypotenuse. That'd be n over n root 2. And that would be true for every sine of pi over 4 or sine of 45 degrees. Okay? You'll see this more than once, so this won't be the only example of this that we do this chapter. These ends are the same number. They cancel. That's like having 8 over 8 or 11 over 11. What does that equal when you cancel something like that? It's when you cancel the same number, like 8 divided by 8 or 10 divided by 10, it equals what again? 1. Okay, I'm not sure I heard a lot of ones there, but 1. When you cancel, you get 1. Canceling is a specific thing in math. So like sometimes people say like 2x minus 2x equals 0 and those canceled. That's not canceling. 2x minus 2x does equal 0. Then they're gone. It makes the x go away, but that's not canceling. Canceling is something in the top and bottom of a fraction, and you make them equal to 1, where it's because they're the same. All right, I can't leave it like that. I got to multiply top and bottom by root 2. And those of you who have done a little bit of trig, do you recognize this fraction, root 2 over 2?
Yeah.
If you don't, that's okay. You'll only see root 2 over 2 another, 1,000 times before this is all said and done. Okay, pi over 6. Do you know what that would be in degrees? It's 30 degrees. And again, if you don't know that now, that's okay. We're going to have a discussion about that later, but that's 30 degrees. And so then we go down to this triangle, and we say, okay, let's go to the 30 degrees. This is opposite. This is adjacent. Tangent is opposite over adjacent. So it's n over n root 3. Again, the ends cancel. And you have 1 over root 3. And again, you got to get the root out of the bottom. So I multiply by root 3. And I end up with root 3 over 3. That would be true for any size triangle with a 30-degree angle. The tangent is always root 3 over 3. Okay, one more of these. Secant 30 degrees. Okay, so secant 30. So let's label this. This is the adjacent side, and this is the hypotenuse. Do you think it's better to do cosine and then flip it, or to just say secant, it would be hypotenuse over adjacent? You understand the difference there? So you could do it either way. I mean, I don't think there's one way that's better than the other, but I just want you to be aware. Some people do cosine and then they flip it. Some people just say, well, if cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent, and they write that down. So you could do either way. I wasn't trying to talk you into one or the other, just to say that there's two different ways to think about this. And then again, you have to deal with simplifying. So I have 2n over root 3. The n's cancel. You have to get that root out of the denominator. You won't always have to get the root out of the denominator.
Wait, how would you find cosine 60? Isn't it cosecant 60? Because you were talking about like you could do cosine 60 instead of secant 30.
Oh, I understand what you're saying. Okay, wait. Yeah. So look, I was talking about these two being reciprocals. Okay, so the secant, yeah, so the secant and the cosine, these are not equal. These two things are not equal. I took this and I flipped it. Okay, the cosecant of 60 is equal to secant of 30, but that really wouldn't make it easier, because cosecant's not any easier than secant. I understand your question. You could probably check it that way. You could do cosecant of 60 and see if you get the same thing. I believe I did the simplifying right there. 2 root 3 over 3. Everybody okay with all this? Okay, now let's go back and do that tangent one, and we'll see how that kind of falls into this category. So it says tangent theta equals 1, and The problem with creating a triangle here is you only have a single number, right? You got 1. So you go like this, you say, okay, there's my angle, and tangent equals 1. But what numbers should I put on this triangle? Here I had a fraction, so I did 3 and 7, but this is just a 1. So what number should I put? 1 and 1, 1 and 1. And it is a 45, 45, 90. Let's say, I went crazy and I put 17 and 17, because 17 divided by 17 equals 1. Do you think that would be okay? Yeah. The tangent theta for 45 degrees is the same for every single similar triangle that's an isosceles right triangle. So I can put any two numbers that divide to 1. Obviously 1 and 1 is a good choice. Let's do the Pythagorean theorem there. What's this side? Oh, okay, let's not do the Pythagorean theorem. Let's do this rule. Then what's this side? Square root of 2. If I did the Pythagorean theorem, would I get the same thing? Yeah, so I said Pythagorean theorem, but I was really talking about just knowing that the rule is n root 2, because if those are equal, that theta is 45 degrees. Now remember what they're asking in this question. They say evaluate the remaining trigonometric functions. We're not going to do all of them to save time. Let's do, what do you think is the easiest one to do? Sine is easiest? I think cotan is easiest. I think in general people like sine the best. But I think in this problem, cotan's easier. Let's do sine theta. So sine is opposite over hypotenuse. So opposite side over hypotenuse. And then you get that root 2 on the bottom. Go like this. And you get root 2 over 2. See, if that 1 was a different number, that number would just cancel. You'd have like a 17 here and a 17 here. They would just cancel and become a 1. So it would be root 2 over 2. I'm going to do one more with you. Cosecant. Cosecant is actually not that bad on this problem, depending on how you do it. There's 2 ways that people would do this. Okay, the long way and then the easy way. So the long way to do it is take your sine answer, flip it, and then get the radical out of the bottom. But the easier way to do it is to either flip this one before you got the radical out of the bottom, or say it's hypotenuse over opposite, which would be root 2 over 1, which is just plain old root 2, which is your answer there. So we didn't do secant, we didn't do cosine, and we didn't do secant. I'll just tell you what they are. They're the same as sine and cosine. It's cosecant. So cosine is root 2 over 2, and secant is root 2, if you wanted to write those down. But that's all 6 of them. All right, find this page. These 2 problems are just a reminder how to do right triangle trig when you are solving on the calculator. You will need to know SOHCAHTOA. You will need to be able to do right triangle trig to find missing sides and angles. So there's a missing side problem. So I'm trying to find this unknown side, and I have this angle on this other side of the triangle. So I would label these. Now I could use this angle. I could find that angle. That angle's 59 degrees. Okay, but why use the 59 when I can use the 31? So this is opposite 31, and this is adjacent to the 31. You gotta pick the angle first. I could have used the 59 degree angle, but I chose the 31. If you pick the 59, those labels have to be different. But I chose the 31. There can only be one unknown, so the unknown is the opposite. I'm going to obviously use the adjacent. So is this going to be sine, cosine, or tangent? Yell it out. Which trig function? Sine, cosine, or tangent? Tangent, because I am looking for O, and I have the A, and of course I have the angle. So I'd say tangent of 31 degrees is opposite over adjacent. If you forget how to solve these, the best way to do it is to think of this as a cross multiplication. I'm going to multiply these, I'm going to multiply these, and it'll just say x equals 12 times the tangent of 31 degrees. I would put that 12 in front. It's always safer to put it in front. And then I would do this on the calculator, 12 times the tangent of 31. Before I hit enter, what do I need to make sure I have? Degree mode. It's in degree mode. I wouldn't use the degree symbol. I wouldn't trust the calculator. I would put in degree mode. If it doesn't say how many decimal places, do 2 decimal places. I get, oh my gosh, I wrote a degree symbol. Okay, I was saying degrees and I wrote a degree symbol. That's not degrees. It's 7.21 is the length of that side. Does anybody know how you can look at that number and say to yourself, you know what, that sounds right, 7.21, that seems like that would be the length of that side. Anybody have any reasoning of why that seems right? And don't say because that's the way the drawing looks, because the drawings, are not drawn to scale. Anybody have any reasons? They raise your hand. Yeah, there's a rule in math that says the smallest sides across from the smallest angle, and the largest sides across the largest angle. And you could likewise say that since this angle is bigger, this opposite side will be bigger than the 31. And you could even go as far as saying, if it's 45 and 45, they're coming out equal. And so if one was 46 and one was 44, they'd be almost equal. And so the farther they are apart from each other, the farther apart they're going to be. So if you had a 1 degree angle and an 89 degree angle, those would be a lot different. I just know it has to be less than 12. I wouldn't know how much less is 12. So if my answer come out 8 or 6 or 9, I think that'd be okay. But if I got an answer above 12, I know something's wrong. Okay, let's read this next problem. Miss James is using an 8-meter ladder to clean the windows on her second floor. So I'm going to draw a picture here right away. You have the ground. You have the ground in a building, and we're going to assume that makes a right angle, the ground in the building, and then you have a ladder. And it says an 8-meter ladder. So that's right, 8-meter ladder. The ladder stands on level ground and rests against the side of her house at a point 7 meters from the ground. So what always happens on these problems, people are not sure where to put the 7. I would describe this leg as the distance from the bottom of the ladder to the house. I would describe this leg as how far up the house the ladder is from the ground. And that's the one they're talking about, 7 meters. It's from the ground to where the ladder reaches. The other one is the bottom of the ladder to the base of the house, along the ground. Okay. The ladder's manufacturer safety manual states that the angle between the ground and the ladder should be between 70 and 80. I just made that up. I don't know if that's actually true about ladders. So, if you're doing something with a ladder at home and you're like, Mr. Pedraza said 70 to 80 degrees, and then you fall off the ladder and get hurt, don't blame me. It's fictional, okay? I'm sure there is some kind of rule, like don't use 1 degree and don't use 89 degrees, but I don't know what the actual regulations would be. But we're talking about this angle, okay? From the ladder to the ground, okay? Ladder, ground, talk about that angle. All right, so if I'm using that angle, this is the opposite leg from that angle, and this is, of course, the hypotenuse of that triangle. What trig function am I using here? Sine. And my unknown thing is the angle. Remember, there could be only one unknown. So I can't use the adjacent side. That's also unknown. The unknown is the angle. And this is opposite over hypotenuse. Now we're going to spend a ton of time talking about inverse trig functions. Inverse trig functions, when you're talking about right triangles, are not really complicated. You do them on the calculator gives you the answer. You don't have to worry about quadrants or domains and ranges. But when we talk about inverse trig functions later in the future, there's going to be a lot more to it than just saying do inverse on the calculator. But for these kind of problems, you just do the inverse on the calculator. It's that simple. That angle can only be between 0 and 90 because it's part of a right triangle. It can't be above 90 or negative or anything like that. And the calculator knows exactly what you mean as long as you type it in correctly. So I do inverse sine, okay? So this is the only time we've really done an inverse in right triangle trig, and you probably have done this when you've learned right triangle trig. And I want to talk about this decimal that you get here, and we'll talk about why people round a decimal like this wrong. Okay. So you can think about what you think it rounds to, and then we'll round it. So I'm going to round it to 2 decimal places. Okay. So the question is, if I'm rounding it to 2 decimal places, is it 61.04 or 61.05? What do you guys think? 4. Everybody thinks 4? Okay. No one thinks 5. All right. Now, what if somebody said to you, like, look at this. There's a 9 right here. This 9 would make that a 5. If that 9 makes that a 5, now behind that 4 is a 5, and we said if behind that number is a 5, make it a 5. So you don't think that's you? I didn't talk you into a 5 right there. But you understand if that 9 makes that 4 or 5, and then 5 makes that a... No, you don't agree with that? Do you see why somebody would do that? Okay, don't ever do what I just did. Okay? That is wrong. People do that all the time. They double round it. They round it 3 decimal places. They take the 3 decimal place answer and round it to 2 decimal places. You round 1 time. And if you ever lose your mind, you're like, I don't know what rounding even is. All you're saying is this, I wrote the wrong answer. All you're saying is this closer to 0.04 or 0.05? Which is it actually closer to if you graphed it on the number line? And it's closer to this number, not the other number. Barely closer, but it's closer to this. And your calculator also rounds for you. So you can change this to you change it to 2 decimal places, and it will round it for you. Everybody good with all that? Okay. Oh, and then we didn't actually answer the question. Is that a safe angle? Yes or no? The answer, the official answer to this is no. It's between 70 and 80. It's at 61, so it is at a dangerous angle according to this fictional problem. Everybody happy with that problem? Okay, we're moving on to something else. Okay, so we just talked about right triangle trig. This is all right triangle trig. Starting about right here. We talked a little bit about the calculator there. But now we're going to talk about trigonometric functions of any angle. So we're talking about looking at a coordinate plane and having an angle anywhere on that plane, and that angle could be positive or negative or above 360 or less than negative 360. So any number that you could think of positive or negative. So we have to talk about how we define angles on a coordinate plane. An angle is determined by rotating a ray around its endpoint. That's just the general idea of what an angle is. We're going to talk about standard position here. And the starting position of the ray is the initial side of the angle. And the position after the rotation is the terminal side. And then it says if an angle is in standard position, and every angle we do is going to be in standard position, if this is the initial side, you can label this. It says if the initial side coincides with the positive x-axis, that's the starting place for all your angles. Okay, so every angle we do, unless you hear otherwise, that will be the initial side where it starts. And then the terminal side will be anywhere on the coordinate plane. Okay, so it says label the initial terminal sides of the angle. I just did that. Coterminal angles, you'll heard this word, coterminal angles, have the same initial and terminal sides. They start at the same place and they end at the same place, but they might rotate differently. So let me give you an example of coterminal angles. I know this is kind of going a little bit fast here, but 370 degrees and 10 degrees are coterminal angles. 370 is all the way around plus 10 extra, and 10 degrees is just 10 degrees of turn. Those would be coterminal angles. You sometimes have positive and negative ones. Let me tell you a little bit more, and then we'll come up with some more coterminal angles. Positive angles have a counterclockwise rotation. Now, that might seem opposite of what you would guess, but this way is positive. And if you think about the way the quadrants are labeled, remember learning about quadrants in algebra? Quadrant 1, quadrant 2, quadrant 3, quadrant 4. They're labeled counterclockwise. And when you learn about them in algebra, your teacher will be like, these are called quadrants, or 1, 2, 3, and 4. And you'll be like, yeah, whatever. And then you'll forget about them, for a long time. And then you really don't talk about them much until you talk about trigonometry, where you talk about them constantly. So we're constantly going to be talking about the quadrants. And they're labeled counterclockwise because that's the direction angles go. They go from quadrant 1 to 2 to 3 to 4 in the positive manner. And negative angles go clockwise. So somebody want to give me another pair of coterminal angles. They start at the same place. They end at the same place. No one's got anything. My example was 10 and 30 and negative, what did you say? 330. Okay, let's think about that. Negative 330 would be turning this direction. It would go all the way around, and it'd be 30 degrees away from getting all the way around. And then 30 degrees would be 30 degrees of turn this way. Those would be coterminal. 30 and negative 330. Can somebody give me another pair? No one else can come up with anything else? 0 and 360 degrees. 360 degrees is all the way around and landing right where you started, and 0 degrees is not turning at all. So those are coterminal. Let's do one more. Have we got anything else? Allie? Yeah, go ahead. They both be positive, yeah. Or both negative. So my example I did was 10 degrees and 370. Let me explain this again. 10 degrees is obviously just a little bit of turn this way. 370 is all the way around plus all the way around plus another 10, which will land at the same spot. So 10 and 370. Go ahead.
So I feel like every single time you want to get back to the same spot, you have to do either a full rotation or go back a full rotation. So
Yes.
Plus or minus 360.
Plus or minus 360. Would you say, Blah, what if you did 2 360s? Would that be okay?
2, 360, 7. Yeah, you could do it.
If I did like added 720. So it's not just adding or subtracting 360 that gives you coterminal angles. It's adding and subtracting multiples of 360 that go give you coterminal angles. And that's all in degrees. We'll talk about radians some other time. But yeah, it's adding and subtracting 360s. And we'll actually write that down later in the notes. So that's what it means to be coterminal. Okay, so we're not done yet. We got to talk about how you find trigonometric functions of angles that are on the coordinate plane. So this has nothing to do with unit circle. This is kind of like right triangle trig, but it's not exactly the same as right triangle trig. So we'll use some right triangle trig ideas here, but this is different because this point could be anywhere on the coordinate plane, except for right on the origin. You know, it says r can't be 0 here. So besides on the origin, from any point anywhere on the coordinate plane. Okay, so draw a right triangle and label this x and label this y. We'll talk about creating these right triangles. If you wanted to find r and you knew x and y, what would you do? So if you knew x and y and find r, so we'll say Pythagorean theorem. Pythagorean theorem is right, and we're going to write it like this. R equals the square root of x squared plus y squared, but that's just Pythagorean theorem. And then if you want to make a note here, that r is always positive. The x's and y's can be negative, but r is always positive. And the way it's written, right, the square root, it never comes out to be negative. So that r is always positive. It says here r can't be 0, and a square root can't come out to be negative. So it automatically says it's always positive. But if you want to write the words always positive, it's not a bad idea. Sine on the coordinate plane is opposite, which is y, over hypotenuse, which is r. Opposite over hypotenuse. The cosecant is reciprocal of that, so I'm just flipping that thing. Sine is adjacent side over hypotenuse, so that's x over r. Secant is reciprocal of that. You guys tell me, what would tangent be? Y over x, opposite over adjacent. So again, I did use the SOHCAHTOA right triangle trig ideas to come up with these. And we are going to use SOHCAHTOA and opposite and adjacent hypotenuse. We are going to use those ideas. It's just that in right triangle trig, you can't have negative side lengths. So there is a difference here. Okay, so I'm going to move this up, and even though this might seem kind of confusing at first, this is really not something that is super challenging if you listen to some of the advice that I give you here. So we're going to plot the point 3, 4. This is a quadrant 1 angle. Quadrant 1 angles are the easiest. Let me move this over. 3, 4. Okay. You have to draw a triangle here. And when you draw the triangle, this is the biggest, most important piece of advice the whole day. When you draw the triangle, you have to draw it the same way as everybody else. You don't want to draw it the wrong way. It could lead to mistakes. So let's talk about some wrong ways to draw this triangle, okay? Some people are going to draw a triangle like this. Do you see that? That doesn't even hit the point, okay? So that's a wrong way to draw it. Because people are just connecting, like here's 3, here's 4, boom, triangle, okay? That's a mistake. The R is like this, so you would draw that first. And you see there's 2 ways to create a right triangle from there, right? There's one up here, and there's a one over here. There's 2 of them, okay? You always do the one that has a leg on the x-axis. So I want you to think of a bow tie shape like this. And we'll refer to this bow tie a lot. You're doing one of those 4 triangles. So let me even highlight this. So you see that bow tie shape? You're doing one of those 4 triangles. So it's got to be drawn this way. There's sometimes you could do it wrong and it still works out okay. But we're never going to want it to be any way besides this. So there's never a time where we have that triangle with the y-axis. And like I said, you might get away with doing it wrong once in a while, but sometimes you make mistakes, so it's just better to do it this way. If you think about how you graph a point, you like do the x number then the y number, and so it kind of makes sense to draw them in those positions. All right, so you do the Pythagorean theorem to find this missing side. What's that missing side? 5. It says evaluate 6 trigonometric functions of the angle. When you do the quiz, you're going to have to do all 6. When you do my math lab, you have to do all 6. If you get that 5 wrong, you're going to have a bunch of them wrong. If you draw the triangle wrong, you're going to have a bunch of them wrong. So it's really important you draw the triangle right. So sine, you now need to know what angle to go off of, right? Because there's 2 angles in there. The angle you go off of is always the one that's touching the origin. That's the one you're using. So I'm going to draw theta in there. This is all positive numbers. So this is just SOHCAHTOA. So you might say this is really nothing weird. I'm doing opposite over hypotenuse. And in quadrant 1, it is just like right triangle trigonometry. It's opposite over hypotenuse. So it's 4 over 5. Secant, or let's do cosecant. Cosecant would just be the reciprocal of that, which would be 5 over 4. Let's just do one more. Let's do tangent. What's tangent equal to? Is it 3 over 4 or 4 over 3? 4 over 3. And then cotangent would be the reciprocal of that. And then there's cosine and cosecant, but we don't need to do all 6. We don't literally need to do all 6. So that's good enough. All right, I'm moving on to number 2. I want to get this problem done, and then we'll be done for today. -5 is in which quadrant? Quadrant 3. Quadrant 3 is where everything's negative. So I label that point -5, -5. When I draw my triangle, I have this as the R value. And I always want to connect to the x-axis, where one of the legs is on the x-axis. You never want a leg on the y-axis. And then I label this -5 and -5. Now, some people are going to be really fast at this. You don't need to do the Pythagorean theorem on this one. A lot of times you do need to do the Pythagorean theorem. This one you don't need to do the Pythagorean theorem. How long is that side? 5 root 2. If it's the same number, it's a 45, 45, 90 triangle. If you do the Pythagorean theorem, it would look like this. And you would get square root of 50, which would be 5 root 2. This one is always positive. So the x and the y's can be negative, but those will always be positive. Now, this is the weird part, okay? This is the weird part, and you really don't have a great way of telling people how to label this. The angle is not this angle right here. The angle actually goes like this. Starts here and goes like this. So the angle is not in that triangle. The angle goes all the way around. And that's why I don't like it when people put theta right there, because the theta actually goes like this, okay? So I say go from the origin. I don't even label where the theta is. So I just say go from the origin. So from the origin, this would be opposite, this would be adjacent, and this would be hypotenuse. The R is always the hypotenuse. The Y is always the opposite, and the X is always the adjacent. If you do it this way, the X is always the adjacent side, and the Y is always the opposite side. Okay, again, we don't need to do all the trigonometric functions. Let's do an easy one to start. Let's do tangent. Tangent theta would be opposite over adjacent. What is that going to be equal to? 1. I mean, do you need to bother writing down -5 over -5? No, it's not worth even writing, but I'm writing it so people would know, how I got that, but it's equal to 1. We might as well do cotangent, because if tangent's 1, cotangent's 1. It's reciprocal of 1, which is 1. Let's do cosine this time. Cosine would be adjacent over hypotenuse. So adjacent, which would be -5, over hypotenuse, which is 5 root 2. And what's better, cancel the 5s first or multiply by the root 2 first? Cancel the 5s. And what do they become in this one? Yeah, make sure you don't lose the negative. It's a -1. And then I can multiply by that root separately. And I have cosine theta equals negative root 2 over 2. And then let's just do secant. So secant, I wouldn't flip the answer I just had. I'd flip the answer that I had originally, which would be 5 root 2 over negative 5. And then I would just figure out that those 5's cancel and I get negative root 2. So that's secant and cosine. I didn't do sine and cosecant, but they're the same two numbers that I just got. So I think that's good enough.